and we're already working with leading national and international waste management companies since the last few years. So first of all, to put it into context in terms of mechanical recycling, the numbers say that we're going to have to triple the amount of mechanical recycling by 2030. And to be able to do that, we're going to need a lot more efficiency, automation to be able to reach that scale in so little time. And this is why I believe that some of these technologies will be critical to be able to scale to this level. So in our side, the area of waste that we target and support the most is the sorting phase, which, as you may know, is critical for mechanical recycling to produce a feedstock that is appropriate. So focusing on MRFs and FIRS specifically, they have different challenges. So one of them is that they have very little visibility on the waste quality. So both on the input that they receive on a daily basis that is fluctuating quite a lot, and of course also on the quality of the material that they produce at the end. Many of the processes in these facilities are still manual, from the sampling that is 100% manual, and of course some of the sorting that still remains manual, and of course that is costly, difficult to recruit for, and can even be dangerous. And lastly, these companies are also facing a lot more increasing compliance, and a lot of regulation is coming in to support better data, more transparency, and so on. But of course, that puts more weight and more work also on these companies. So are there ways to be able to scale that? So when we look at how these kind of data gathering methods are done today, as you can see, this is highly manual. We sample around less than 1% of the waste. This is very consuming. It's time consuming as well. So it can take multiple hours before even we have the results of that waste composition. So very difficult to translate into the operations of the MRFs. And so this is why automated analysis is really key, because it allows to obviously look at 100% of the waste, be fully automated and in real time. So talking a little bit more about that, this is why we created at Grey Parrot an AI waste monitoring system that provides real-time analytics on the waste flows primarily in sorting facilities. So as you can see, this is a very simplified schematic of a MRF, but we place our cameras at the start of the operation, at the in-feed. We obviously place them at the end of the product lines, before the balers, before the bunkers and the balers, and also in the residue line to be able to monitor what is the outfall, what are valuable materials that might be lost. And of course, on the audit cabins as well, to replace that manual sampling. And all of this is then translated into a dashboard. So how does it all work, right? So AI always seems very complicated. So to simplify it a little bit, let's go over the system and how it works. So first of all, we place camera systems on top of the moving conveyor belt. So these are completely retrofitted. They can move on high-speed conveyor belts. And then our cameras track every single piece of waste. So they take millions of images of the waste flow and track every single piece of waste that is there. And with that information, we export that information through the cloud and output that into a real-time dashboard that is accessible on any device on your desktop and very easily accessible. That same information can also be translated in different ways and integrated in, for example, robotics, different machinery, financial forecasting systems. So this doesn't need to be a standalone way of looking at the data. So now getting into kind of the real images of how this works. As you can see, this is an example of a waste stream, a real waste stream where there's obviously overlapping waste, dirty, it's dark, it's dusty, as we know, and the models are able to identify each of those items and classify them. So as mentioned, we look at 100% of each item on the belt, and then we categorize them in more than 49 categories. That is exactly the same categories that the MRFs and the PERFs use to understand the contamination levels, the purity levels, and ultimately the waste composition. And today we're able to do that at a 95% plus accuracy, and in most cases, less than 1% error in terms of estimating the composition itself. Of course, this means that with AI, we're able to tackle quite complex issues. So for example, black plastic, as we know, are very difficult to identify. So as you can see, the models are able to really track that on the belt. We also go into details, for example, in food grade versus non-food grade, which obviously is critical for mechanical recycling to be able to create food grade level materials and feedstock. So here, as you can see, we're able to do that differentiation as well. And same on HDPE bottles as an example. And finally, not only the material, but we're also looking at the brand recognition. So for example, here identifying that this is Fanta, this is Coca-Cola, this is Highland Spring, or this is Coop, Tesco. So obviously this is maybe not critical in the actual operations of the MRF, but we are seeing how this could impact EPR, how brands are being monitored, and potentially understanding a little bit better the level of recyclability of some of the products and how products are designed in a way that they actually end up in the right place in these facilities. So if we compare a little bit AI computer vision to other potential vision systems that you may have heard of. So first of all, we have digital watermarking that is very accurate. So where you print items on the packaging itself. And of course, this is very accurate, but on the financial side, this is very expensive. As for the manufacturer, they need to change their packaging. And on the reading side, those cameras are still very expensive. Up to date, and in most of these facilities, you'll find NIR optical sorters. So again, they are good at differentiating different types of polymers. And I'm sure we'll talk a little bit more about this later. But of course, they don't look at the packaging in its whole, right? So multi-layer packaging, black materials, food versus non-food, all these more complex nuances are difficult to integrate. And so finally, the differentiation here with AI and computer vision is that, first of all, the camera systems that are used are very affordable, and this is very scalable. So it's an order of 10 to 20x cheaper than maybe some other hyperspectral cameras. And of course, we're able to go into these very differentiated nuances, and it's models that can adapt through time. Of course, these technologies are not isolated, and they can work together as well. And it's actually the combination of these technology that is very powerful. And in this case, you'll hear about with Andy and Blue Vision later, and Grey Parrot and us are, and Grey Parrot and them are also collaborating on integrating these different technologies together to make an even more effective solution. And so moving on to then, once we have that data, this is where you see the dashboard. So again, this is usually on very manual Excel sheets that you're able to see this information with less than 1% of the waste. And here, what we give to the MRF operators is the ability to see in real time what is happening in their plants. So the purity, the contamination level, we can break down the waste in count, obviously, but also in the mass estimation. We have real-time access, so which is really important for the day-to-day operations, with alerts that can alert from and provide triggers if the contamination goes too high, for example, but also historical insight. So understanding where are the trends, what is happening, what is the feedstock we're creating, do we need to upgrade our plants in a certain way? So really being able to make highly data-driven decisions based on the insight that we're getting both in real time and in retrospect. And we believe this is going to be critical to have more automation to gather this unbiased data, and also much more adaptability, because as different mechanical recycling solutions and even further chemical recycling solutions come to market, we're going to have to be able to produce a product that can be customized to these different types of solutions. And of course, we need to make the MRFs and the PERFs as financially viable as possible. And having this level of optimization also allows to increase up to 20% the margins of these companies. So this is, as mentioned, already deployed in different places. So we're already deployed all around Europe and also in parts of Asia, like Japan and South Korea, with leading players in the sector who have really helped us refine our product and really enable them to add value to their operations. So I'm going to go through a few examples here just to make it a little bit more visual. So this is in a PERF and a plastic recovery facility in Italy with A2A. And as you can see here, our cameras are placed in their end of line product. And here we're allowing to control the end product quality and ensure that the contamination levels are not going too high. This is a use case in Austria with Digido ARA, where we're placing our camera systems just before the balers. And as you can see on the dashboard, on each bale, we're able to see the different composition, and that allows to create a certification of each bale and a guarantee to their customers, so the recyclers and the processors, that the product that they're producing is up to the quality needed and is corresponding to the right purity level. This is an example here with Suez, where we worked on not only the material recognition, but also the brand recognition to understand the recyclability of some of these products, and for them to identify the products that had less recyclability and more difficult to sort, to again report that back to the start of the value chain so that we can make the changes much more upstream. And finally, this is a bit of a different example here, where we integrate our vision system with third-party machinery and robotics. So this can be robotic arms, for example. So this is with the largest integrator in South Korea, ACI Chemical, who are integrating our vision system to provide robotics and automated picking of some of these materials, once again, to increase the purity of the end product. And so this is obviously for commercial purposes that this is being used, but as mentioned, the government and policy is also pushing towards much more data. And so today, as we know, EPR is going to come into play very soon with significant uptake in terms of the financial exposure for the packaging industry. And this also means that for the MRFs, the sampling requirements are going to become much higher. So today, they report on every 125 tons of waste, and that will be moving to every 8 tons of waste. So DEFRA has already indicated that automated visual detection technologies will be key to be developed as a mean of automating and standardizing the future of collection of data, as an example. And it's been great to have a collaboration with them to inform them on how technologies can work to be able to improve the policy. So, and I'm sure we'll come back to that debate later on how that dynamics works between technology and policy. And so moving further into that topic as well, we see essentially the need of much more granular data being critical in the policy that's at play. So first of all, with the plastic tax coming into play and our need to increase a lot more the supply of secondary material, of course, we're going to need much more efficiency and better data on the source of those materials. When we think about the rollout of DRS, and we need to differentiate there between what is food grade, the size of the items, the products with or without label, and so on. And so again, this is where technology can really support that data and that implementation of policy. And EPR, this is more of a question mark, and probably we can talk about this later in the panel. If we had much more granular data at SKU level in the products, could this encourage modulated fees and implementation of EPR in a certain way, and ultimately help recyclability of packaging in a much more effective way than we have today? So that's a question mark, but we do believe that ultimately with better data, we can create a better policy and much more accountability as well. So yeah, this is just an example of how that differentiation could be made. And so again, our goal is really to be that data provider, not only for the waste managers, but also for the wider ecosystem of the circular economy, to help increase recycling, but also help with recyclability and circularity of products. Thank you, and I look forward to talking further after at the panel. Thank you very much.
Okay, thank you, Michaela. Thank you. I still, you know, I do this for a living, and I'm still struck by, you know, the potential of the technologies that you're developing. You know, having run or been part of a team that ran a recycling facility that was reliant on high-speed sorting, so heavily reliant on manual sorting, and just the possibilities of the data. Just fantastic stuff. Okay, moving forward, our next speaker, welcoming to the virtual stage, is Divya from a company called Fiberite. Again, remarkable company based in Wales, currently stitching together all sorts of sort of cutting edge technologies, their own and working with partners, to really ramp up what can be achieved, the range of materials that can be processed and captured from different streams. Fantastic innovation. Divya, please take it away.
Thanks, Nick, for that introduction. Hi, I'm Divya. I'm head of research and development at Fiberite. And our aim is to achieve the end of waste. And our motto, don't burn it, don't bury it, use it, really alludes to the fact that there are so many resources still going to landfill and incineration. We want to recover these, upgrade them, and return them back into manufacturing for the circular economy. From our compositional analysis of the different waste streams that we've been streams, and primarily it's polyolefin-based plastics, so your polyethylene and polypropylene, with a bit of PET as well. So we all know about the plastics challenge. You know, there's not very much recycling. Boris said it a couple of months ago, recycling doesn't work, but it's because the infrastructure is not there. And this is a nice graphic from Suez, and it shows that even if there was 100% public participation in recycling, you have losses because the collection coverage is not 100%. You have inefficiencies in separation by householders. There's losses again at sorting, and then also losses at reprocessors. So in all, you're getting about a 30%, 33% loss of resources, even with a very efficient system. And the other thing is each of these processes is carried out at a different location. So you've got quite a high environmental burden as well of processing, and then the residues that are produced at each stage. Sorry, it's just a bit slow. So as I said, this whole system and the current system is really reliant on public participation, and we're not going to get more materials in the system unless the public is sorting them, or companies are sorting them. You've got the inefficiencies across deal with film plastics, flexible plastics, because they're very bulky and lightweight, and often they can get separated with the paper, so you get contamination in the paper stream. And then also when these plastics are recycled, you often go into lower quality downcycled applications. So how are we addressing this challenge? So what we're doing is capturing resources lost to recycling. So they're not even seen by the recycling system at the moment because they're going to incineration or landfill. We're capturing contaminated, difficult to recycle materials. So anything with food residues, paper residues, multi-layers, multi-materials, that kind of thing. And we're doing the whole process on one site. So from black bag all the way through to high specification product. You know, it's a sustainable and circular approach. We're also providing a completely new source of recyclers, this new untapped seam of material. And then most importantly is we're working with manufacturers and off-takers to really look at their specifications and make sure that we're making products that work for them, so that there is a home, there is a market for everything that we produce. So going back a step, how do we do it? So we've developed our proprietary HydroCycle technology. And what this is we take the waste and we pulp it, so we debag it, and then we pulp it down to break down the organics, so the paper waste and the food waste. And then using water as a separation medium, we're able to wash those organics from the other inert materials like metals and plastics. And then we use different unit operations to recover each of the material streams. So, you know, we recover metals, glass, PET bottles, sort of standard recycling, DMR. Then we also get rigid plastics in the form of pots, tubs, trays, flexible plastics through plastic bags, pouches, film plastics, the paper and card coming through, not just traditional paper and card that goes into recycling, but also contaminated, so food contaminated, coffee cups, pizza boxes, Tetra Pak, that kind of thing. And if there is food waste in that residual stream, it's being solubilized in the water stream, And then that water is processed by anaerobic digestion to make renewable energy in the form of biogas. And we get a clean water out, and you have this, with that water just circulates in the process. So we have a closed water loop process. So we can get at these homogeneous material streams, but actually, and we commercialize this process actually in the US, but what we found is it's just not going high enough up the value chain, and especially after China closed its doors, there's no real value to these commodity grade materials, and these need further sorting. So the last couple of years, what we've been doing is working on bolt-on technologies. So either that we've developed internally, or we're working with key technology partners to take each of these material streams and upgrade them into higher value plastics, materials, energy products, or chemicals and fuels. And as I mentioned at the top, we're doing this all on one site. So our site in Swansea, we're hoping to have this sort of center of excellence where we can show all the way from that mixed residual waste through to high spec product going into a remanufacture. So we've been lucky enough to get funding from Innovate UK for their demonstrator program for the Smart Sustainable Plastic Packaging Challenge. So thanks, Nick. And so that's scaling up the process in our site in Swansea. So here we'll have our hydrocycle process where we recover the resources, and then we also recover rigid and flexible plastics. And what we're finding from our initial composition is actually we're getting quite a high spec polyolefin, so between 80 and 95%, regardless of the composition of the feed stream coming in. Then we're working with a technology partner, Impact Recycling, and they've developed a BOSS system, so it's a baffled oscillating separation system, which uses water again to separate out the different polymer types within the rigid plastics or flexible plastics. And they also have two other systems which are in development to separate out PET and other polymer types as well. So integrating them together, we can get different cuts of polyolefin. We can go through to very high purity HDPE, PP, LDPE flakes. And then we're also working with offtake partners, Molding Solutions, Renella and ProAmpac, to really help us, to guide us with the products and making sure that they are market ready with all the materials that we're recovering. And so we also work to a tiered quality specification because, you know, as you go through to that 99% pure polyethylene, you are going to have residues at each stage of sort of separation. And so there'll only be a portion of material that goes to that really high quality spec that can be extruded into pellets. But the lower spec polyolefin rich materials, they still need a home. So again, we're working with partners and looking at different outlets where we can use the different types of material. So for example, for the film plastics, if we get sort of a 80% polyolefin type plastic, it can go into plastic lumber or damp-proof membrane, decking, fence posts, those kind of applications. So really making sure that we don't have any losses and rejects and have a home for everything that we process. And again, it's all based on this demand-led innovation so that we have off-takers for each of these fractions, and we can make sure that they can go to market. So we have set up our facility at the site Westfield Industrial Estate site in just outside Swansea in Wales. So we're located in this bit of the building here. We currently have our small scale hydrocycle demonstrator there, which is 15,000 tonnes per annum. And within the next year, we'll implement the larger scale facility as part of the demonstrator project. And that will input about 60,000 tonnes per annum feedstock. We're also building the flexibles wash lines, rigid wash lines, and putting in the BOSS technology as well over the next couple of years. At the moment, our key feed stream that we're focusing is on MRF rejects, or rejects from recycling facilities. It's a bit of a misnomer that they're called rejects because actually they are perfectly valuable materials. They've just been missed by inefficient sorting systems in MRFs. And in the UK, there's upwards of 600,000 tonnes of this stuff. So there's a huge amount of material that's just going to incineration, but is of perfectly good value to be recycled. So it's an easy feed stream to access, and that's where we're beginning. But we will then later on also process RDFs, MSWs, and then harder to recycle streams. The other thing we're doing is delivering real system change, especially within films and flexibles. So today there's about 311,000 tonnes of municipal film arisings across the UK, and about only 6% of that is collected, and only 1.6% of that is actually recycled in the UK. So it's a really tiny amount. So even our demo facility, where we'll recover up to 13,000 tonnes of flexibles, will increase that recycling level by 65%. And then our ambitions up until 2028 will mean that we can increase flexibles recycling, 300%. That's a huge impact that we can make with not very much infrastructure. And then the plant will also address a 30% recycled content by providing a new source of recyclate to go into manufacturing, and then 70% of plastic packaging effectively be recycled. So anything that comes to our plant will be effectively recycled. So as Michaela and Nick mentioned, there is a huge changing regulatory framework around this whole space. So how does that affect us? There we've got, as it was mentioned, there's deposit return stream coming in, increased film collection, plastics tax, EPR, and then the outcomes of the Basel Convention. And yes, all of these will have an impact in changing the composition of the current system happens to be, because as I said, it's all reliant on public participation, and so there will always be plastics in the residual stream, and especially the next 10 years, it's not, yes, there will be changes, but there will still be material for us to recover and put back into the system. So it's complementary to the current system, and it's robust and it's flexible. And even now, we're seeing MRF rejects, but every facility is producing MRF rejects of a completely different composition, but we're getting quite consistent output streams. And then lastly, just want to touch on the sustainability of the process. So across the UK, recycling rates have stagnated at about 45% over the last 10, 15 years. And no matter what governments are doing, these don't seem to be changing. Wales is better, they're about 65% average. But then you have these EU targets of 65% by 2035. And even though Brexit has come about, we're still signed up to try to meet these targets. And there's a real disconnect as to how we're going to go from that 45% through to 65%. But if you start implementing technologies like ours, then we can already cover 70 plus 80% of materials. And with the MRF rejects from the stuff that we've been doing at the moment, we're showing 95% recoveries. So, you need new technologies that are better at sorting and better at segregating to help close this gap. Also, the carbon footprint of the process. So the materials that we're recovering, they would usually be going to incineration, some to landfill. So for every ton of RDF equivalent waste, you'd be producing 400 kilos of carbon dioxide. Whereas if they go through hydrocycle, we're saving about 380 kilos. And then this is even more pronounced when processing MRF rejects, because the MRF rejects have upwards of 60% plastic or more. So, and they would be going to incineration. So they have a huge carbon footprint really when they're incinerated. So for every ton of MRF reject, you're producing about 900 kilos of carbon dioxide. Whereas if you put it through our process, you're saving about 800 kilos. So a large plant, we have the equivalent of removing about 20,000 cars from the road each year. So this is reporting the carbon savings per ton of waste, but we can also report it per ton of a product that's produced. So if we're producing a ton of rigids, they would save 2,200 kilos of carbon dioxide for that ton. And then if that ton of flake is used in on-road manufacture, that carbon saving is then passed on through the supply chain. So you're reducing the carbon footprint of the whole supply chain. So thanks for listening. Hope that gives you a good overview of what we do and what we're trying to do. Please follow us on our social media channels and on our website and stuff, and get in touch if you've got any questions. Thanks.
really. See the equipment going in. It's going to be great. Okay, moving right along. So next we're sort of flipping around again, and we're coming to Andy, who's joining us from his company Blue Green Vision, focusing in, no pun intended, Andy, cameras, specifically on a thing that's been touched upon by both the previous speakers, but is felt throughout all of the automated mechanical recycling and sorting. You keep hearing that word, sorting. The best quality recycler comes from the best sorted material. And absolutely fundamental to the process of sorting is our cameras, our ability to differentiate between types of polymer, colors of polymer, other materials. And when coupled particularly with the kind of super sophisticated AI systems that companies like Grey Parrot are developing, they can really transform the capabilities of facilities like Fiberite and, of course, Biffa operate. It's all interconnected. So I shall now hand over to Andy and please tell us about Blue Green Vision. Thank you.
Okay, yes, thanks very much for that introduction, Nick. As Nick sort of said, Blue Green Vision and its sister company, which is Face Photonics, we work in this region, in the sort of technical area of spectroscopy. We are essentially a company that is dedicated to building spectroscopy systems, and so we actually build the base spectrometers ourselves often, and develop those into systems which are targeted towards use cases. Our expertise as a company is in sort of optics, in electronics, in illumination systems, in software and algorithms. So we're very much a kind of sort of almost like a sort of an electronics product manufacturing company. So the kind of products that we've built for sort of industrial clients, I've given you a sort of selection here of 5 different products that we've built. Starting on the left, that's actually a system for the food industry. It's designed to be integrated onto one of their lines, and it detects things like protein content, fat content in dairy products, in meat products, and things like that. So the reason why people are sort of turning to spectroscopy is we essentially are looking at the base chemistry of any material. All of our products in all of the different industries that we work over are always focused on identifying the presence of material, measuring the presence of material, classifying what material something is made from. And what Blue Green Vision and Face Photonics do is we focus on the actual sort of detection systems of all the technologies which are related to those detection systems. So we don't build sort of end machines. We don't build machines which have got conveyor belts on them. We don't build robotic arms which have grippers on the end to pick things up. We don't build air jet systems to blow things off conveyor belts when they've identified them. We are exclusively focused on spectroscopic methods for identifying materials. And what we try to be is we try to be the experts in that bit of the value chain. And then we work with partners, whatever, who are going to develop the full solutions. We work with clients who come to us with a problem. We've heard things like PVC is a huge problem for us in our process. If there's some PVC, it destroys our downstream chemistry. Can you build a system which can eliminate PVC for us? So what we will do is we'll look at how we're going to detect the PVC and provide an identification system. We'll alert people to when there's that material in their system. Okay, so that's a little bit about us. I'm going to very, very briefly, I imagine many people already know a lot about this, but just talk a little bit about the sorting machines themselves. As I mentioned, we use spectroscopy. So every material, based on its sort of chemical composition, the energy levels in its composition, will absorb a characteristic set of photon energies or wavelengths of light, different colors of light. And here on the left, whatever, I've got a graph which just shows you some different reflectance spectra from different plastics, and each different plastic material type has a different set of peaks. So for example, if you look at the polystyrene, the PS graph, the second one from the top, there are two nice closely spaced peaks right in the middle of that. And that's a beautiful signature, which is a good way of identifying polystyrene. So and the idea of the spectroscopic method is that we're going to identify materials by their chemistry. So we're looking for that unique spectrum. And then what we do is the spectrum comes out of the machine, and it could have some offsets. It's the distance that the bit of plastic is away from the sensor could be changing. It might be slightly contaminated and things like that. So what we then have to do is we have to try and pass that through some kind of mathematical algorithm. And the point of the mathematical algorithm is that it gives essentially a score to each point that it measured. And if we design that algorithm correctly, we can differentiate between different material types. So here what we've done is we've taken 100 samples of PET, 100 samples of PE, we've put them in front of one of our cameras, and we've passed the data through the algorithm that we use to differentiate between those two material types. And we get essentially, this is a histogram of the scores that we got. So we got a lot of PE scores, above 90, whatever, towards the right-hand side. We got all the PET scores are below about 20, 25 at the left-hand side. And the beauty of this is, this is an example when it's working really, really well. There's a huge chasm, whatever, in the histogram between the two material types, and it shows that we're able, with 100 samples of each type, we were able to 100% of the time differentiate between these two classes of material. I have to confess that this is done in sort of laboratory type conditions, or whatever, almost not quite laboratory type, not sort of like clean laboratories, but sort of office type conditions really. It doesn't necessarily take into account the full level of dirt that you get in a MRF and things like that, but the principle, the underlying measurement is there. So if I move on, so this is an image which many of you will be very, very familiar with. It's a sort of standard sorting machine. This one happens to come, the image I borrowed from Fanuc, who are putting one of their yellow robots very prominently on the image. The identification system is at the far end of that belt as we look at it. The material's all coming towards us on this photo. You'll see a bright stripe of light going across the conveyor belt. It's at that point that you're going to identify the material, and you've got maybe a second or two to identify and classify the materials, by which point the robot has to know where it has to go to pick something up. It doesn't necessarily need to be a robot on the end of this. I've mentioned that you can use blowers. You can also actually illuminate an object over which you want a human to take off the conveyor belt. So that's again, sort of an optics type solution that is very, very easy for us to implement. If we kind of take a sort of little bit of a look at the identification system, what we're doing is we're using a thing called a push broom hyperspectral camera. That in simple terms means that for every point across the width of the conveyor, essentially we take a photo, and with that one photo, for every single point across the width of that conveyor, we get an independent spectrum. And then the conveyor moves on a little bit, and essentially we get a next stripe of data. So we were going to reconstruct a photo by taking slices of the image one by one, but instead of just doing a simple sort of a red, green, blue, or a black and white image, we get a full spectrum for every one of those points. So that's the idea of push broom hyperspectral imaging. In order for this to work, we create a very nice intense line of light, whatever. We don't want to illuminate everything. We're only going to be looking at one very thin region. So we create an efficient, bright illumination, so we get nice clean data going across that. And again, our expertise is in knowing how to set this thing up, is in designing the hardware in order to be able to get good clean data out of the system. And then basically this is just sort of showing it's the sort of the steps. We take a photo, get a spectrum for every point along the image, the conveyor belt moves on, take another one, and then we gradually build up the image in that way. So once this has been done, you can take essentially a conveyor's worth of rubbish, and on the left-hand image, it's imaged in the visible, how you and I would see it. And in the right-hand image, it's how the hyperspectral camera can see those. So essentially, it's produced a false color according to what material type everything's made from. So that's the information that we can provide to to machine builders, to recycling facilities, to whoever's essentially the customer for that information. To give you a sort of the idea of a typical system, we would often run our camera at 600 frames a second. It'll have a 640 by 512 pixel detector on it, which means that we arrange the 640 pixels to correspond to the full width across the belt. For every point on that belt, we get a spectrum. And then if for example, the belt's moving at say 3 meters a second, every 5 millimeters along in the movement direction, we get another spectrum. So that gives us some kind of idea of the resolution, the granularity of the data that we're able to produce. That means that we're going to have a lot of spectra to analyze, and there's essentially of what materials are coming along and what position on the belt. Essentially, that's our role in the system. Over. Okay, Nick asked me to talk a little bit, and I think this is possibly quite interesting for people who are taking on new challenges, who are finding the problems with existing solutions. A little bit about the new directions that these the scope for improvement over existing ones. The first one is all related to the detector technologies. Essentially, a lot of the detector technologies were originally developed for, say, military applications, but they're gradually finding their way into sort of civilian uses. If we look at all the different wavelengths, essentially different detector technologies are sensitive to light at different wavelengths. The standard sort of silicon detectors that come from sort of everyday cameras. Then there's some InGaAs materials, so indium gallium arsenide, which are in the standard sort of NIR sorter. So if you got a sort of standard TOMRA NIR sorter, it'll have an InGaAs detector in it. More recently, essentially there's a thing called an extended InGaAs. They do some clever steps to the chemistry of the InGaAs detector, and they're able to push the wavelength range out to be a little bit longer. So if the standard InGaAs detector will work from say 900 to 1700 nanometers in wavelength, the extended one will get out to about 2300 or 2500 nanometers. And in that extra window, there's quite a lot of spectral features which can be used to identify the plastics. Here I've put a little sort of tick beside the ones which we already have solutions for, but we think that there's a really interesting region going beyond. Well, we're already covering some of it with our extended InGaAs product, but there's a really interesting region beyond the range of current NIR sorters, where we know that there's chemical peaks there. There's a lot of work being done, particularly with black plastics. There's a range which is normally referred to as the mid-wave infrared, MWIR. And we're very, very interested. We think we've worked out how to produce a system which will be extremely effective in that region. So if you'll excuse me one shameless plug during the presentation, we'd love to work with somebody who would like to try and develop a solution for that. We know that there are some early devices coming out in that, which are incredibly expensive, but we think we've got a very, very cost-effective solution in that. So apologies for the shameless plug, but we'd love to hear from you if that interested you. Okay, if I just move on. All of the things which I've been talking about today, so far in the presentation, have been related to essentially collecting reflected light. So we're shining lights down from our light source onto objects on the conveyor, and we're collecting the light that's coming back up, so it's being reflected. That's not always the best technique. There are some alternatives. You can do transmission spectroscopy. Often that would require putting the materials on a light colored belt, or there's another nice technique which you do where you actually allow the materials to cascade off one conveyor onto another one which is slightly lower, and during the moment when they're in free fall, you can actually make a transmission spectroscopy measurement. There's another completely different spectroscopy technique called Raman spectroscopy, which has wonderful sensitivity to all kinds of different materials. It's used a lot in the pharmaceutical industry because it can detect the presence and the relative concentrations of lots of different chemicals at once. It does have some disadvantages. The signals coming back are incredibly weak normally. So it's quite a challenging technique in some ways, but it could have some interesting applications. And there's a third one there, which is called laser-induced breakdown spectroscopy. It's LIBS. It's referred to as a microdestructive test, because what you do is you zap the product with a small pulse of laser energy, which vaporizes a very small amount of it. The vapor, while it's sort of in a sort of plasma-like state, emits lots of light and is particularly good at detecting the atomic composition of a material. So if you're looking for one particular element in a material, then it works very well. It can be used on things like metals, which are often quite difficult to detect using spectroscopy. Essentially, most metals are just shiny and have very, very few features in the normal bits of the spectrum. So metals can quite often be detected and identified, and alloys can be identified and detected using LIBS. So again, we're not married to just doing reflection spectroscopy. The third area I wanted to mention was essentially it's combining the techniques that we use with other techniques. Michaela described a lot about the advantages of their AI-based solution, which has many advantages or whatever. It has the possibility to identify whether or not a waste bit of plastic was from a food source or a non-food source. So it can start to detect the origin. It has a few weaknesses as well. For example, when you get pieces of film, a film of a random sort of torn shape can't be identified easily by its shape. So there's essentially a film is one of the types of material that we can identify really well. It's got a nice uniform thickness. It's normally got a reasonably good area. We're able to identify the base material from that very, very well. So there are areas where you might want to essentially combine the different technologies and essentially use you've got more data, you've got more statistical evidence to identify different bits of material. And combining the two, whatever, does offer the potential for a sort of, a next level sorting system. So what we're working with Grey Parrot is essentially how do we produce something which is very, very cost effective. One of the nice things about the AI-based system is the hardware is not very expensive. Therefore, for the front end of a material system, essentially, if you want to identify, say, 60, 70, 80% of your materials before they go on to any more sophisticated, more expensive sorters, it's the most cost-effective way of doing it. So can you build an even more cost-effective sorter, particularly at the front end, and particularly when you're trying to gather the data on all of the materials coming into a plant. There's lots of sort of advantages around that area, which we think that the combination could be beneficial for. So we're working with them on that, and hopefully maybe next year we've got some exciting news in that front. So if you've got a new application, if you've got a problem material, if something's not working particularly well in a recycling facility, how might Blue-Green Vision be able to help you? We normally sort of break any projections. There might be the presence of water or something like that present. Then what we'll try and do is we'll use existing equipment that we've already got without building anything new, and try and make a representative measurement. We'll try and establish whether or not spectroscopy can help you in your sorting or materials identification problem. So that would normally be a relatively short sort of viability study, but doing that enables us to essentially specify in detail what equipment would be necessary to tackle that problem. So with that information, we would give you an accurate system specification for something that we could build, which will work at an industrial level. It could even work at a handheld level, and work with you essentially to make sure that that's going to be easy for you to integrate into it. And then lastly, we'll be very, very supportive of the implementation and testing and helping you try and get the data. We'll try and work with you on algorithms and things like that in order to to monitor how well the system's going, how well it's performing, and make sure it's a successful project for you. But again, we're just one part of the overall project. We don't build the machine, we don't run the facility. Essentially, we're with the identification sort of experts that hopefully you can rely on. So I think I've got to click once more to get that to appear. Yes. So basically, what we do is we build the hardware. We know how to put it in the right places in your systems, and we can work with you on the data algorithm. And then we pass that on to you for whatever mechanical or chemical or other processes you want to do with it. So yes, thank you very much.
Okay, thanks, Andy. Absolutely fascinating. And I'm going to be thinking about Pushbroom for quite some time now. Libs as well, quite like that one. It was fascinating that in the early days, the plant I built, we had a Raman spectroscopy based flake sorter, and I remember being told that one of the hardest things was just being able to process the sheer level of information that it was able to detect and feed into the systems. Amazing. Right, moving quickly on to our final speaker in this session. I'm going to introduce Phil Goodyear from Managing Director of the Polymers business part of Biffa. Phil, over to you.
Thanks very much, Nick, and great to spend time talking to everybody this afternoon. I'm going to split this presentation into two sections. The first is just a brief introduction to Biffa Polymers, but then I guess in the context of the session we're in, more importantly, the second half about the future and challenges of mechanical recycling and some of the strategic and technical challenges that we're wrestling with. Just a bit first on the Biffa Polymers business. You'll know about Biffa as a waste management company. That's where our brand is well known, but we're actually the UK's largest plastics recycling business in food grade. We have 3 manufacturing sites in the northeast of England. We employ just under 300 people. It'll be nearer 400 by the end of this year. Big focus on food grade with HDPE and PET recycling and non-food grade polypropylene. We really paved the way with the dairy industry in the UK in food grade HDPE recycling. The business turns over about £130 million, processes over 125,000 tonnes of input material, and sells about 85,000 tonnes of polymer. The difference between those two numbers is yield loss, which is a big economic driver for the business. We've got great long-term customer relationships with the big brands and the packaging converters. And I'll chat over the next few minutes about the critical success factors in a successful mechanical recycling business. I'm not going to talk about Biffa for any length of time, other than to say that a big strategic strength we have as Biffa Polymers is our upstream skills and scale in collections and sorting. So I'm part of the division of Biffa that also runs MRFs and PERFs and energy from waste plants. But upstream of that, we collect an awful lot of recyclable materials, and the fact that we collect it and we sort it in our own MRF and PERF network. And my own colleagues are the people I deal with on raw material supply and quality and process improvements. That's a massive source of advantage. We buy very little spot bales. 90% of our feedstock comes from within the Biffa network. And we enable a true closed loop recycling model. This one shows, as an example, what we've done for years with the dairy industry. And we're rolling the same model out into the PET, carbonated soft drinks and mineral water industries. Just a bit about what we do and where we do it. Where I am today is our original site in Redcar in the northeast of England. The primary focus here is food grade recycling of HDPE, and the majority of the customers there are the UK dairy industry. At the moment, we make about 20,000 tonnes of output product. We're in the middle of a big expansion, and we'll take that to about 30,000 tonnes a year. And that will be the end of our journey in HDPE, simply because beyond that, we're feedstock limited in the UK. We have a fantastic facility at Seaham, about 30 miles north of here, where it's a state-of-the-art, the UK's largest single-stream PET recycling facility. We bring about 1.4 billion bottles a year into that and produce about 30,000 tonnes of mainly PET pellet, a small amount of flake. And we invested just under £30 million a couple of years ago to build that facility. And then nearby we have a polypropylene wash plant, and that is again a new building, a new site, and lots of space there for future expansion. I mentioned that I would chat a bit about critical success factors, and there are three things we always talk about in our business. The first is manufacturing excellence and the skills we have in managing and deploying projects. Essentially, we build these recycling plants using our own engineering team. We don't go out to EPC contractors for this. And a skilled group of people with a background in engineering and manufacturing take our experience from one plant and move it on to the next. And we've got a huge amount of expertise in the food safety protocols, going right back to our original work with the dairy industry in the UK. I've mentioned feedstock. It's really important, both in terms of security of supply, security of costs, but also increasingly management of quality, because if we have a quality issue, I'm talking to colleagues and friends rather than across a commercial barrier. And clearly our customers are the people who pay the bills and drive the growth and success of the business. And we have long-term contractual relationships with major brands, and we either supply directly to the brands or to their converters. This tends to be under long-term supply contracts with a de-risk commercial model where we have essentially an element of tolling fee in the commercial arrangement, so that ourselves and the customers are less exposed to commodity price changes. We work with lots of large brands, and that list is expanding all the time as we grow in PET. So that's a bit on the Biffa business, but just chatting a bit about what's going to drive the need for and the way in which we behave as a mechanical recycling industry. I think these are factors that are known to everybody. We've got EPR boosting demand. The plastic tax has fundamentally changed commercial behaviour in our industry, and the number of new inquiries we're getting at the moment from small users, purchasers of packaging, who suddenly realise their costs are going to change by 30% in a few weeks. DRS schemes starting in Scotland, they won't just increase supply, but they'll change and improve the quality of the feedstock. The brands and the converters are far more interested in sustainability, and when they get it wrong and come under attack from NGOs, from their customers, from social media, it's big trouble. So it's both a positive and a negative to manage, which is it's a key measure of business performance. Capture rates are increasing, and it's becoming a lot harder to move plastic across national borders, as we all know. So the plastic that the UK generates is increasingly going to need to be recycled and reprocessed here. And just a bit on technical challenges. I've split quality into two areas. The first one is purity and consistency. Our approach here is to focus very, very hard with our upstream perf partners within the Biffa organisation on feedstock quality. Clearly, if you're expecting an optical sorter to work to a very high standard at a very high rate, it'll do that much better if it's having to sort less stuff out. And essentially, our downstream quality is fundamentally a function of the input quality. We are investing in state-of-the-art sorting capability and increasingly moving across the perfs and Biffa polymers to the use of AI and robotics. And the robotics move is partly Britain is going to be increasingly difficult. So robotics is partly around process capability, but it's also a financial and human resources reality. The second quality area is food standards. and these clearly are incredibly tough standards. This is all about understanding the key driver PE, and fundamentally the brands are looking for things in much more detail than they have done traditionally. So we're talking in some cases parts per billion levels of contamination when we're bringing in dirty mixed feedstocks, and that challenge of going from an input that's sort of 70% pure to an output where impurities are being measured and controlled in parts per billion is a heck of a challenge, and you have to be really good at managing that and understanding what really matters. The issue about recycle and downcycle, fundamentally food grade in, our aim is to make food grade out. There's a problem on polypropylene that we might want to come back to in the Q&A, but in HDPE and in PET, we really don't want to send it out of food grade, because once we've done that, it's been lost to the recycling network. But the recycling process produces an element of collateral and sorting losses. We get in our PET bales, we get non-PET, and the aim there is to downcycle the non-PET polyolefins into non-food grade products. And then the other really important thing, and we can't change this, we can just influence, is design for recycle. And that's about influencing and educating the brands and packaging designers about how their design impacts on recycling. And I've put influencing the consumer in brackets. It's a laudable aim, but in reality, it doesn't happen fast and it's not perfect. So our primary work here is with brands. And just some examples here of some great things that have happened. Clear milk bottle tops. So putting the sort of skimmed, semi-skimmed differentiator, the red, green, blue differentiator on the label rather than on the cap means that the cap becomes clear, and the clear HDPE cap is then recycled along with the bottle. That simple change is a significant yield improvement. In the middle, Lucozade Sport, our important partner Suntory, some great work done here. Initially, the removal of PVC from the over label, that full length sleeve is now completely recyclable, but it's a film and it might be recyclable, but it isn't recycled because it's rejected in the plant. And over the next few weeks, they're moving to a much smaller, easier to recycle label. And you've got much more PET as a total percentage weight there. And on the right is an example of how it can go wrong. I don't know if any of you have come across the comedian Joe Lycett. He did a fantastic documentary on Channel 4 with a sort of broad-fronted assault on the Yacht brand and its use of a non-clear white PET bottle, and the fact that is not recyclable. And that brand, under essentially a social media barrage, changed their recycling. But thermodynamically, if you can mechanically recycle, it's the way to go. Some of the challenges, as recycled content increases, the product just becomes more and more grey, and there's actually very little you can do about that. You can with PET, you can reduce this effect by removing PET jazz, or coloured PET, both from the supply chain and from the process. But no industrial process is 100% effective. So if jazz goes in, some will get through. And as it goes round and around the loop, everything just gets grayer and grayer. And the same applies to deposit return schemes, PET that you see in Austria and Germany as well. That is also quite a grey polymer. This dream that people talk about, 100% recycled 100% of the time, it's actually technically not possible. You do need a purge in a mechanical recycling process. Otherwise, as things go round and round the loop, contaminants just build up. And also, there is a small amount of damage to the molecular structure. So there's a limit to how many times a PET or an HDPE bottle can go round the recycling loop. That at the moment is being masked by the fact that recycling and recovery rates are quite low. But as they move higher, this challenge gets harder. And there's definitely a role in working in partnership with chemical recycling to address that challenge. Previous speakers talked about flexibles and films. They can be recycled. At the moment, not many of them are being collected, and the sorting infrastructure is not designed to deal with this at the moment. We're going to need segregated collection systems and different sortation technologies. Moving things around with air jets is fine if you've got a dense material, but with a very light film, it's not particularly effective. PET trays are a concern. We do recycle 100% PET trays, but multi-layer trays are a problem, and they cannot currently be recycled. And deposit return schemes are very positive, but they're not a panacea. They improve the quality of the product, but they don't eliminate some of these issues with graying and molecular damage as the thing goes round and round the loop. And just to conclude my own thoughts and where we're trying to take the Biffa Polymers business, the things that we're focusing on in the next few years, we're really keen to expand our PET business. We've completed and commissioned the first plant in Seaham. We're looking to build a plant that's essentially designed around DRS material, and the initial focus there is on Scotland. Mentioned films and flexibles. We will make a significant move there in the next 18 months. Chemical recycling, I suspect our role will be as a feedstock supplier. I doubt that we'll be running big chemical recycling facilities. It's not really our skill set and competence. And we are cautiously looking at opportunities outside the UK as well. That is all. I hope you found that useful, and thanks for listening.
Thank you, Phil. Absolutely great stuff. It takes me back to in fact, really interested to see the clear milk bottle cap thing. Spent many happy hours buying and fitting flake sorters to take out the green and the red and the blue flakes. And remember, again, work that we did in partnership with Biffa as was, Closed Loop as was, and some of the other dairies on trying to identify why recycled HDPE had a slightly green tint to it. And the fact it's because it's semi-skim milk is what we would enormously drink. And if we wanted slightly pink material, we just needed to encourage everyone to be healthy and move on to red cap. Okay, I think we can bring the rest of the panel back together. There we go, the Muppet view, as I like to refer to it. I'm going to very quickly say thank you very much to all four of our speakers. Remind people, which I was supposed to do before I introduced Phil, and I forgot, that there is a Q&A function, and we have Anita with us, who's feeding questions from the Q&A into our little audience area. We've got a few questions in, which I'm going to go to. Let's have a look. Okay, so first question from Veronica, talking about mastic tubes and silicon tubes, or silicon the material, or issues on sorting lines. So Andy, is it a question about the ability for you to detect those? And I think after that, Andy, I come to Michaela as well around the idea that in some cases, things like that read to some systems as just HDPE, and the opportunities for you to be able to identify, absolute problematic packaging items, because there's nothing worse on a recycling line than a half-filled tube of caulk that goes into the granulator.
Yes. So question relating to materials like silicones, mastics, other types of polymer. I don't know the specifics about where in the spectrum you'll be able to detect those materials, but every material has its own characteristic spectrum. A silicon bond has a different energy to a carbon-carbon bond. For us, it would be a question of looking in the literature to see if there's some spectra available in the public domain. If not, getting some samples, testing them, and very quickly, within 1 or 2 days, we'd be able to tell you, yes, we can spot something which is characteristic of this material or isn't. But almost every single time, we can find something in there which gives it away almost.
Thanks, Andy. I always remember a project we ran where we tried to teach our optical sorters to recognise, don't know if I should mention individual brands, let's say a particular form of isotonic sports drinks orange label, which we knew had a clear PET bottle underneath the sleeve. So if we could get them in the right place, we knew there was lots of good PET. Michaela, how precisely might you be able to target, you know, things like cork tubes that are just terrible things to get into a recycling process, or some recycling processes? Oh, Michaela, you're on mute.
I'm back. There we go. So first of all, I think there's further a general question that's posed first for us, which is, can somebody see it with the human eye, even a very, very expert human eye? And if the answer is yes, then we can integrate it into an algorithm. And so even with what we've done, we started with 20 categories of weight and expanded that to 50, and we're now going to 100. So we can get more and more granular and more detail in all these nuances. If this is something that is absolutely not accessible to a human eye, even in an expert human eye, this is where, again, integrations like Blue-Green Vision or other types of technology can be beneficial to have another input. And the thing is, the combination of both makes that much cheaper than if you rely just on one or the other technology. So in a problem like this specifically, a bit like Andy, I would want to see exactly visually the problem, how it's presented, and then I think that guides us toward what's the best solution there. And a bit referring to your comment on Lucozade there. So for example, on that use case, we had seen in the data that we were tracking, which was not public, at months before they changed the packaging, that was an issue because consistently those materials were ending up in the residue. So that such a problem would have been identified with data much earlier on, had this been tracked on a much more regular basis. So thought I'd refer to that as well quickly.
Okay, thank you, Michaela. Right, another question. One I think probably directed mostly at Biffa. Are you having any issues with limonene in the PET? I remember limonene always used to worry us in the HD line because nobody wanted lemon flavored milk. But I don't remember seeing it in PET. But are there any particular problem things that would be eliminated? There is another question actually around glues and adhesive residues that come from labels, and if packaging was designed better, we might need to wash less and things like that and use fewer chemicals.
Limonene is we look for it. It's not a difficult one. It's not. Tiny amounts of residual PVC and benzene, and if you sort hard on PET, your benzene goes down. If you sort too hard on PVC, you've got a big yield loss in your flake. So there's a really tough balance there, and I completely agree with the concern around glues. We have this wonderful shiny new plant, and the bit of it you really don't want to go anywhere near, despite the fact it's brand new, is the wash plant, and it's where we have all of our sort of operating challenges in terms of blockages and breakdowns. The question here talks about excessive use of caustic soda, which I agree with, but also any glue breakthrough into the final product is going to cause a concern with haze and other product quality issues. So if we can just get rid of glued labels and move to perforated seams, that will just be fantastic. It's happening. That will just be fantastic for wash plant performance.
Okay, thank you. Right, I'm going to take the opportunity to dive in with a question of my own. And all of you, in your own ways, are innovating. Whether it's developing specific technologies or suites of technologies that can do stuff better within waste and recycling, or you've got a new technology or a group of technology, you're trying to put them together in a plant, or you're running a major waste company and trying to sort of keep up to date and keep abreast of what you can do. what holds you back? What drives you forward? You know, is it being able to try stuff at scale? Is it financing? I'd be really fascinated to hear sort of your insights, particularly because hopefully we've got people watching that maybe have got a bright idea and wondering how they might be able to take it forward. In no particular order, but I will start with Divya. Sorry, Divya.
Money, it's always money. But for us, especially to do things at scale, it's just the finance. And I mean, this money from Innovate is great, but we still have to find, we have batch funding from investors, but getting money from a Welsh Development Bank and things like that is proving quite difficult because it's still seen as a risky technology.
Okay, Andy, do you want to come in?
Yeah, there's a sort of I don't know if I'll get it quite right, but there's an expression which is necessity is the mother of invention. For us, that's the case. Come to us with problems, and it's often the case that we've got a particular viewpoint on things where we can solve it. Go to visit Grey Parrot as well. They might have a different take on it. The different problems, one of us will probably have the better solution than the other one. But yeah, we're essentially a component manufacturer, so we're quite a long way away from the coal face or the plastic mountain or whatever you want to be. But yeah, come to us with the problems, and we can try and solve them.
Okay, Phil, how about what's the overall approach to sort of the next big thing at Biffa?
Well, first of all, we're incredibly positive about innovations. My background prior to this job was CEO of a biochemical startup, so I understand the venture-backed sort of startup approach. And then before that, I worked for very big chemical companies. In the chemical industry, you have R&D functions and you have pilot plants. We have neither. In Biffa, that's changing and changing rapidly, and we are now experimenting quickly with robotics and AI. But generally, there's a culture thing that we don't like to buy serial number one, and also because we don't have a pilot plant, putting it onto our big plant that's running at 160 tons a day, if it goes wrong, it's damned expensive. So the ability to experiment and pilot stuff, or the inability to experiment and pilot stuff, I have to say is a personal frustration. I'm relatively new to this job, and I'm not used to that. And so it's about how we take safe baby steps with new technologies and gain confidence and go again. Because I think an approach of just saying we won't buy serial number one is wrong. It's too blinkered. But we're also not going to take a massive risk on an unproven chemical recycling technology and invest. Companies and new technologies navigate the valley of death, so they can pilot technologies, so we have confidence in them, because we're not going to invest in that. We're not in general, unless it was truly revolutionary, going to put equity into something like this. We will wait until it's essentially battle proven, and then we will implement it. And the other thing is, one very practical thing is often space. So if you're looking at something like putting a robot in, you might not have space on the conveyor because there's an existing picking station there, or there's an existing Tomra or Poulenc optical sorter just where you want to put your robot. And practically, that can actually stop you or make it incredibly difficult. It sounds easy, but creating space on a conveyor production line can be really, really expensive.
Yeah, fascinating stuff. I remember years ago being asked to, we would get asked if someone could to see how 1,000 of their new label bottles, where they ended up through our sorting lines, or one time even just capturing video of belt footage, which could be looked at. It's very disruptive in a very low margin business where you really are trying to run 24/7. Michaela, how about yourself? Your experiences of working with they're not you either love working in perfs or you don't love working in perfs, but it's always an experience. How do you find it?
There we go. I was going to mention actually the commercial adoption and being able to work with early adopters is very critical. I think when we're in your new company. I mean, in our case, we're lucky that we are causing minimal operational disruption, and that's part of our product offering, is that we don't cause any changes in the operations. So that allowed us to work quite early on, even when we almost didn't have a product at all, with quite large customers. That helped us refine the product and what we need to do. So I think that's critical, because if you're able to prove the demand and the need and the solution and the technical proof point, then raising capital on the back of that is much easier. So I think that's really the starting point, is proving that you're able to respond to a real problem that customers are having. And then from a capital standpoint, we've had a mix of grant funding with Innovate UK that's been incredibly helpful, but also venture capital as well, because obviously the scale of capital you can raise there is larger and is much faster. So I think a combination of both is quite important. And from the venture capital side, I would say there's a huge gap between what they think about investing in sustainability or innovative solutions and their understanding of complex industries like waste management and plastic. So there's a lot of education to be done on the investment community on the complexity of these issues. So, but again, having early customers.
Okay, thank you, Michaela. So I've one eye on the time. So I think we could make a last and simple question to each of you in turn. I'll start with Divya, then Andy, then Phil, then Michaela. If you could sum up in one word, and I'll allow a couple more words, the future of mechanical recycling, what would you say, Divya?
I'd like to say Fiberite.
That's fine. Good answer. I think that, very, nice one. That's a good one. I'm going to say that before I come to Andy, Phil, and Michaela, I'm not going to allow you to say Fiberite, nor your own company names, but I'll let Divya away with it. Andy. Oh, Andy, you're muted.
Being a long way from the coalface, a bit of a difficult one to answer that. I don't know, the better. I see detection technologies getting better and better. There's some really great stuff coming along. So adopt, I suppose, would be my one word.
Thank you very much, Phil.
2 words: bigger, better.
Nice, nicely done. And finally, Michaela.
I'm going to say much more adaptable and resilient to change, and digitized as well.
Excellent. Well, that's absolutely fantastic. I don't know what word I would say. I'm going to say the future's bright, but I think I'm contractually obliged to do that. So I'd like to say again, I'd like to reiterate my thanks to all 4 of the panelists. That's been absolutely brilliant. I'd like to thank the audience for tuning in and for putting in your questions. I'd like to thank the events team for making sure everything's working in the background. And the only last thing to say is please keep engaging. There's, I think there's at least one more session in today's schedule, and the rescheduled quiz will be at the end of the day. If you go into the event platform, you can find, if you've missed sessions, you can rewatch. You can schedule your sessions out for tomorrow. You can connect with other people, other attendees on one-to-ones, visit virtual booths. There's so much here to see, and we're only just, not even at the end of day 2. So thank you very much, everybody.